Okay, next we're going to extend our discussion to what are called non-inertial frames of reference. Basically, we've talked about problems when our coordinate system, that is our frame of reference, our xy, is sitting still, or when it's moving at constant velocity. Those are what are called inertial frames of reference. And if your coordinate system is moving at a constant velocity, including a possible velocity of 0, then Newton's laws will work the same way wherever you are. But if you have a non-inertial frame of reference, that's a frame of reference, a coordinate system that's accelerating, then you have some very interesting things that happen. So if you remember, we talked about with relative velocity problems, the coordinate system on the ground versus the coordinate system on the train that was moving. And we said that that was something that we could do, but we specified that the train had to be moving at a constant velocity. So now we're going to look at what happens when the train is accelerating. And that will give us a coordinate system that's accelerating, and that provides us with a non-inertial frame of reference. In fact, it doesn't have to be a train. Any coordinate system where you're accelerating makes Newton's laws seem to not be accurate. But in reality, they are accurate. You just have to know how to use them. Okay, in the previous video, we saw how an elevator accelerating upward can create an apparent extra force, the weight. So the reading on the scale would go up if the acceleration was going up. Now, that real force comes from the elevator being accelerated upwards. It's actually pushing on the scale, which is pushing on the person to accelerate the person upward. So there's a real force. But from the perspective of the person in the elevator, they just feel heavier. It feels as though like there's a force in addition to gravity pulling them down. There's not really somebody up above pushing them down into the scale to increase the reading, but it feels that way. Because in the real world, if you're just standing on a scale, what you feel is the normal force pushing against your feet. That's how you experience your weight. And so to the person in the elevator that's accelerating upward, they feel that extra force pushing against their feet, making them feel heavier. And that's a fictitious force. It's not really a force that's pushing them against the scale, but rather the scale is being pushed upwards against their own feet, and they get this Newton's third law kind of reaction that's pushing back. And so that's why we call it a fictitious force. Gravity hasn't suddenly become stronger. There's no magic pushing them down from above. It's just the fact that there's an acceleration. And if we imagine a coordinate system that's glued to the elevator, that's accelerating upward with the elevator, from that perspective, it seems like there is an extra force, but in reality, there is not. Let's see if we can take this idea and make it a little bit more clear. Imagine a person on a rocket, far away from the Earth, so the Earth's gravity isn't affecting anything, and they're accelerating upward. And what if they accelerate, so their rocket ship accelerates upward at an acceleration of little g, 9.8 meters per second squared? What would happen is, now again, there's no Earth here creating gravity, but the rocket ship is accelerating upwards. The scale is pushing up against their feet. They would get a reading on their scale that would be equal to their weight. And so this would create a sense of artificial gravity, and to the person in the rocket ship, it would be exactly the same to them as if they were standing on the surface of the Earth. If they did an experiment, they would measure exactly the same thing that they would measure on the surface of the Earth, whether it be with a pendulum or shooting a projectile or whatever on their ship. They would feel a force just like the force of gravity. There's not really a force of gravity again. This is a fictitious force created by this accelerating frame of reference. This xy, the coordinate system that is moving along with the person, is creating the sense that there is this extra force. Okay, so let's consider two possibilities. One, we have a fixed coordinate system, and two, we have the coordinate system that's moving with the ship. And so our blue system is the fixed coordinate system, and the green one is the one that's moving with the ship. And so I have this guy, and of course the rocket ship is firing, so it's accelerating upwards. And this guy is holding a ball up and he drops it. Now, what happens is the rocket ship moves upward. And so a second later, or however long later, the rocket ship has moved upward. Now notice, the ball is in line with the blue coordinate system, and according to Newton's first law, there's no actual real force acting on that blue ball. So what's it going to do? It's going to stay right where it is. It's not going to accelerate. And so on this later picture, you can see that the fixed coordinate system hasn't moved and the ball hasn't moved. It's still lined up with the origin of the coordinate system. But the rocket ship has moved out from under it. And so to a person following the green coordinate system moving with the rocket, to them, it looks like they dropped the ball and the ball fell straight down. It's as though there was a force of gravity pulling the ball to the floor. Now, again, there is no real force of gravity. This was simply caused by the motion of the ship. The ball itself didn't actually move relative to a fixed coordinate system. But relative to the coordinate system that's moving, it does have relative motion. And it would fall with the acceleration of the rocket. The faster the rocket was accelerating, the faster the ball would drop. And if the rocket were accelerating at little g, this would be just like living on the earth and dropping a ball. Now there's an insight that we can make here, a key idea. In an accelerating frame of reference, Newton's laws are not valid. So here we have our ball, we let go of it, it seems to fall as though there were some force, but that's entirely caused by this moving coordinate system. There is no force, but from the person in the ship, it's like there was a force there. So what that means is even though there's not a real force, in this moving coordinate system, the ball accelerates downward. Now, Newton's law says if there's not a real force, there can't be an acceleration. So in the frame of reference of this green coordinate system, Newton's laws are violated because there's not a force actually acting on the ball. In the fixed coordinate system, the ball stays where it is and Newton's laws work. The fixed coordinate system's not accelerating, it's a valid inertial frame of reference. The accelerating coordinate system is a non-inertial frame of reference, and Newton's laws do not work in a non-inertial frame of reference. So the question becomes, what can you do if you have a non-inertial frame of reference, if your coordinate system is accelerating? And the answer is, you can do one of two things. You can either pick a fixed coordinate system and just work your problem like normal, or you can use the non-inertial coordinate system and you can pretend that there's a force acting on the ball. Because if this green coordinate system is accelerating upward with little g, this ball will behave inside this rocket as though the force of gravity really were pulling the ball down. And so all you have to do if you're in the rocket, accelerating with the rocket, you don't have to find a star out here to use as your fixed coordinate system. You could just pretend that gravity works and work everything normally and you would get the right answers. Now, so our key point, non-inertial frames of reference, that is coordinate systems that are accelerating, can give rise to fictitious forces like our artificial gravity. Note bien, that's French, it means note well. Here, this fictitious force, sometimes called imaginary force, is always in the opposite direction from the acceleration. So if the acceleration is up, the imaginary force is going to be down. Interestingly, this idea of a non-inertial frame of reference is one of the things that led Albert Einstein to one of his great insights. He pondered these questions and he imagined what would happen to a beam of light passing through the window of an accelerating spaceship. And so you can imagine the beam of light normally would go straight, but if the spaceship is accelerating upward, from inside the ship it would seem like the beam of light would curve downward. Now, light normally travels in straight lines, but in this accelerating frame of reference, it seems to curve. So one of the things that Einstein reasoned out was he argued that if this artificial gravity caused by this non-inertial frame of reference causes the light to bend, then real gravity should cause light to bend too. In other words, a beam of light should bend if it passes by something really heavy, like a star. And in fact, almost as soon as Einstein made that prediction, people looked for it and they were able to measure that. In fact, that is what happens. When a beam of light passes by a star, it bends because of the gravity of that star, which is actually pretty darn cool.